Hello, let's get this blah blah. Hello, let's get this show rolling. I'd like to start off today with Matt Metz. Matt is a longtime electronics hacker. Normally, when you think about making PCBs, you're thinking, oh, painstaking hours dragging the traces around. Or maybe you're one of those auto router fanatics. I don't know. Painstaking hours dragging traces around. But But what if you could turn it all into a simple matter of software? And so he's going to be talking about scripting your way into circuit boards. Yeah, sorry. Scripting your way to circuit boards, which opens up, of course, all sorts of avenues for generative circuit board foolery. So without further ado, please join me in welcoming to the Hackaday Europe stage, Matt Metz.
Sweet. Thank you for the introduction. Hi, I'm Matt Metz, I'm going to talk to you about some little tool we're working on to build generative, geometric boards. So first, here's what I'll cover quickly. A bit about me, some challenges we've been having that caused us to want to spend time making a tool, and then I'll talk to you about the circuit program, go through a tutorial about it, and then open up for questions. So about me, I run a little electronics design and manufacturing studio with my partner Hong Hong, and we're based in Amsterdam now. Previously, we were based in Shenzhen, and we do everything from small electronic board design to actually producing things in-house. We have a little pick-and-place line, and so we get our hands on all parts of the electronics design process. We started making these geometric PCBs in 2014. We launched this project called Blinky Tile, and we did a little Kickstarter for it. And this was a series of metagonal boards on a PCB. And this was each board had one LED, and the shtick was that when you solder it together, the soldering points are also making the connections. So you can form the structure just as you're sort of soldering it together. But if you've done circuit board routing before, you understand that putting a bunch of weird stuff like these pentagonal pieces onto a board is kind of frustrating. And so we did this manually, and we had to draw out a bunch of lines and use a CAD program to match stuff up. And it was a huge pain, but we got through it for a single piece. But then we never made a variation of it. We never made one that was bigger or with more sides because it was just too frustrating, and I didn't want to deal with it. So we made this. It was a lot of fun, but then we kind of left it. And these were some examples of things you could make with it. You don't have to make a small ball. You can make these larger sculptures. This one got installed in X Factory Seed Studios thing in Shenzhen. And then these are some more examples of projects that we've done for clients. So we work a lot with designers who are building huge sculptures, maybe 1 or 5 meter things, and they would go in fancy lobbies or nice houses or something. And they're all made with these circuit boards. One of the person, Jason Krugman, that we work with for a long time, he's a designer that builds these things, and we do the engineering work for him. And he's building these structures that are entirely made out of circuit boards. So the whole sculpture is just circuit boards with LEDs on them and hardware to hold them together, and that's the whole thing. And when we're making his projects, they're sort of like geodesic domes. So you need to have 3 or 4 sizes of PCB that are all slightly different, and you might have one that's 150, 170, 175 millimeters, and then 178. And we've been making variations of this for him for maybe 7 or 8 years. And for a long time, I was just standing there. Every time we would do it, I spend 2 hours, and I open the design up in my schematic editor, or in my PCB editor, and I'd select everything, drag it over 2 millimeters, select the next thing, drag it over 2 millimeters, and then the last one is another millimeter. And anytime we make a mistake, it's 1,500 euros to make a new set of boards. So it's really annoying, and it's very painstaking process. And then we also make these flat boards. The one on the left is for a guy named Teddy Lowe, and it's this spiral pattern that went onto 8 PCBs. And the PCBs are all identical, but they have this pretty terrible routing on them. And so normally in our program, we can generate the locations using a program. Like with this one, I used a processing program that told me where all the LEDs should go. And at least with that, I could drag around sliders and say, you know, LEDs look like this and look like that. But at the end of the day, processing just gave me a nice like table of parts number and then like the rotations and then the location they had to be. And so I sit there for the next 2 hours dragging one LED over, looking at its spot in the table, and then like moving it around. So it's a huge pain. So we were thinking about like, we tried a bunch of things like trying to script Eagle or something before, but it was all painful. And basically like everyone's making circuit boards with a CAD program because that's like what CAD programs are for. But practically like if you're making a circuit board, you really are just trying to make some artwork that's in a special fancy format. So you need a couple layers. You need an outline to show you what the outline of the board is. You need artwork on each layer. So you need 2 copper layers at least, a top and a bottom. And you need like a silk screen, solder paste. And for us, because we're doing a lot of manufacturing in-house, we really care about things like the solder paste stencil, because small changes in when you put down solder before you put it into a reflow, when you're making a board, can cause a huge difference in your reliability or in your output. And so that's something that we really try to take care of. And it's something that works really well in a design tool because you can manage, you can say like, I want to update all the footprints on my board to match this new one we did. And you can be relatively sure that you got it. And so that's one thing that we really wanted to use a tool for. And then you also need, of course, like locations where you would drill holes to make vias. And so if you wanted to do sort of the alternative route, I don't know, has anyone used like SVD to Shenzhen or Gingerbread here? Yeah. These tools are awesome. They're really great, and they make you like, they're absolutely the best thing to do to make like artistic PCBs, because you can use design tools like Inkscape that are designed to make geometric patterns rather than dragging around lines of circuits. And the only real disadvantage we saw with these ones is that we wanted to be able to control things like our footprints. Like we wanted to know that like when we made this LED this specific way, in when you put the LED on the board, the footprint for it has to be just right. And for us, this is important because we are producing these like in mass. If you're making a couple, you can just make everything big and then do it by hand, and it's no problem. So the major reason why we were frustrated by these tools is just that we wanted to integrate our artwork with like a DRC check, right? So fortunately, KiCad is a pretty awesome tool for doing circuit board design. And it turns out that the engine for the PCB tool for it is PCB new, and it's a library. So actually, they publish bindings for it. So you could actually just script with it, and you can do anything that you can do in the GUI with a script. And the only issue with it is that it's really designed to power their GUI, which means that anytime you want to open up a project and start something, you have to do 15 things. You have to like make an object and then assign something to an object and connect everything. And so you can program it, but it's frustrating. But what I really thought was I wanted something more like processing. And has anyone used processing? It's a pretty great tool for doing like creative coding, right? Because it's an environment that's based on Java, but in fact, you don't really have to think about Java at all. You just have 2 functions. You have one for setup and one for draw. And then everything you do is just like draw line, make something. And if you do find out that you need something more complex, it's actually just Java, so you can start importing things and make it work. So it's a tool that like really does a good job of just hitting exactly what it needs to do, but also not getting in your way when you want something more complicated. So yeah, so the goals for that is I wanted to make a like creative coding PCB library that would have very low complexity. So you'd only need a few lines of whatever language it's in to start a board, build it. And so I also didn't want to go down the trap of making a PCB tool that does a lot of things for you because it's very hard. So something like our LED layouts are very simple. They're just things that are repeated over and over, and they don't take a lot of specialization each time we're making them. Whereas if you're trying to make an IC tool that connects up every pin on your microcontroller, that becomes very difficult very fast, and it's never going to work for almost anything you want to do. So basically, we wanted to make a tool that will handle like 100% of a very simple board or 80% of a complicated board, but not get in your way to make the less 20%. And so I made an API for Python, basically, that wraps the whole PCB-new engine and gives you like geometry-style interface to it. And so, yeah, installing it is pretty simple. It works. We haven't tested it on Mac, but it should be fine, and it works in Windows and also in Linux, of course. And it's on pip, so if you've used Python, you can just do pip install circuit painter, and it shows up. Okay. And so I'll give you a little tutorial about how to make a simple board. So this is like a minimum viable program to make a circuit board that spits out something that is like in KiCad that you can use. So basically, if you used Python before, you use you import our library, then you create a painter, and then the way that it works is you're sort of drawing lines or circles or arcs onto some layer. And so the first thing you want to do with the board is you need to make an outline for it. So you switch to the edge cut layer, which is what PCB uses for, or KiCad uses for storing the outline of a board. And then you can just draw a rectangle, like 0 to 0 to 2020. So in this case, we're making a 20 millimeter by 20 millimeter rectangle board. And then you can use the preview function, which then just launches KiCad, and you can see you've got a board here, and then you can verify in the 3D tool that, hey, it's a rectangle. This would be very quick to do by hand, so there's no reason to use my scripting tool for this, but that's the starting point anyway. And so then a little more complicated things. There are shapes. So we made rectangles, lines, circles, and arcs. This is an example of how to do it with the silkscreen layer. So if you switch to fsilk-s, that's the layer that puts it on the top. All these things like the rectangle, line, and circle, the way KiCad works internally is it has different kinds of things for things that are conductive tracks and things that are just like geometry. And so these ones, the versions of these ones that I'm showing here with rect, circle, and line, these are only making non-conductive things that are visual. But there's a version of this that's also just like track line or track arc, which make conductive paths. So you can choose both of those. And then you can also do things like changing your line width. We wanted to make it so, I guess this is entirely just copying how processing works, right? But the idea is that if you wanted to make lines of different lengths, you don't pass it in each variable. You can just set a sort of like an immediate mode program to change the line width. So here I've got one that's just showing you 3 lines of different widths. And the trick is you just call width between each one. And that's great. And you can also do fills the same way. So you can make filled rectangles or non-filled ones. And that also works if you're making like a copper plane on a board. But then the part that's fun is because this is just in Python. So with a small amount of scripting, you can start to create patterns that would be like reasonably difficult to get on a board. And so I introduced 2 different things here. The first one is this translate function. So the circuit painter also has a transformation matrix in it that supports translations and rotations. So if you wanted to repeat something across the board in different ways, you can just do translate, rotate, and you can also push the matrix or pop the matrix. So you can like start at one point, move your reference plane over here, draw something, then move it back, then move it over here and draw another thing and keep repeating like that. And then for parts, you can do footprints. And by default, it's using the KiCad library. So you can use any part that's in KiCad. If you want to find out what are the names for them, you just open the footprint editor in KiCad, and it gives you a list of all the different parts. And so you choose which, I think like family, and then which part you want to use. And you can put them down. So at the moment, the circuit painter isn't handling nets. So you have to tell it how you want to connect something. So in this case, I've got a resistor and an LED. And so I had to connect them with ground, and then I'm calling a net called LED, and then LED to VCC. And that's how they're connected. That's how they go down. And then, of course, just the parts by themselves don't really make a connection. So in this case, I am adding a track, or 2 tracks and a via to draw my 2 components, and now I've got connections between them so they can be electrically connected, and do that. And then you can do something more complicated. Like now you just run a for loop with translations, and you can put a bunch of LEDs here. And you can still do this by hand, but it's kind of a pain. And if you wanted to change something, it's a huge pain to go through and like move everything. And the nice thing about this is like if you decide you want more LEDs, it's not a problem. You just change the variable name, or you change the loop, and you get more. And then, right, actually, this previous code has an error. So when you're making a board, I've got a bunch of these LED resistor circuits, but when I made the script, actually it's connecting all of the connections between the LED and the resistor. I gave them all the same name, so KiCad thinks that they're all connected together. And so it'll give you an error with the DRC to say, hey, you haven't connected all these nets that you said you were going to. So to fix that, we can just give each net a unique name here. And so I'm just using the name of the variable to do that. And then now everything is fine, and that's what it looks like. And then, right, to finish up with this, basically, you can say, actually, I want the board to be a little bigger, I want to have more LEDs, and I want to make all these lines around the edges. And now it's just a couple extra lines here. And then that's, right, it would spit this out. And then again, you can just change it. For most of these ones, if I'm not making a demo code, what I'll do is I'll either make a command line Python function that takes in arguments and says, like, you can just type in like LEDs equals 20 on it. Or I started to do now like web interfaces for them. So you can do all of this, and you can get a SVG at the end. So I make a little Flask web server in Python that lets you choose all the parameters for your board, and then every time you change something, it actually calls KiCad, builds a whole board, and then gives you the preview in the board, or in your web browser. So it's self-contained. And the preview function down here is only showing, it saves everything to a temporary directory when it's running KiCad. So it doesn't cloud up your computer because you have a script, so you shouldn't need to keep all the intermediate files. But if you want to save, there's functions for saving out just to a KiCad file or to a Gerber, which pops up as like a zipped Gerber file you can just send to a fab directly, or a series of positions if you're doing pick and place, so you know where all the parts are. And then the nice thing is when you call these functions, it's also calling the DRC check for you, so you can find out if you made any errors that are critical. And all that is well and good if you're just doing something that's a bunch of LEDs and resistors that are stuck together. So we made one, where did it go? Here. Before the talk. Actually, on Monday, I got from Eisler, I ordered a bunch of these boards using a similar script to this one. And I haven't tested them yet, but I've got 20. So if you want to come and assemble one later, let me know. And this is great for this kind of board. But if you want to do more complicated things, it's actually fine too. So my friend Trammell is the first user of this project outside of our internal uses. And he made this awesome trolley watch. It's a version 2 of it. The first one he made was a couple years ago. And again, he made it once, and then he just stopped because it was impossible to change it. But this time around, he rewrote it to use Circuit Painter. And all of the edge parts and all the LED components and all the parts that go in the rings are all generated geometrically. So he could change, like he wants to say, like maybe it's 35 millimeters wide or 40, and he can kind of tweak that around. And then he has a little microcontroller on this. So for the microcontroller part, he did that in KiCad normally. So he drew a little microcontroller and connected it up to the names, and then dropped some parts in. And then the way that works is KiCad generates, the Circuit Painter generates a KiCad file that has a group of all of the parts that it made. So you can either edit that file directly, or you can just copy that group into a circuit or into a new KiCad project, and then add your own parts. There's still some problems with it. So right now, as far as I can tell, the KiCad's PCB part is well scriptable, but I don't think that the schematic entry is scriptable. So right now, this program is only generating a PCB. So if you want to make a schematic, you're kind of on your own. If someone knows how to do that, I'd love to know, because I'd love to also spit out some sort of schematic to go with it. But we're not doing that at the moment. And then there's some other trickery. So if you're doing a board like this, if you wanted to start with a schematic and draw, if you wanted to be really sure that you connected everything correctly, you could lay out in your schematic all the parts and connect them. And then when you run Circuit Painter, you have to figure out what the internal UUIDs are for each part, so that you could link the schematic to the PCB. And that's another thing that we don't have a good workflow for yet, but we would love to have. So that would be especially useful for this project, because he wanted to be sure that he has this crazy Charlie plexing things right. It was right, but yeah, it took a little bit of effort to make sure. So yeah, that's that part. And so thanks. If you have any questions, yeah. Yep. Yeah, so anyone? Yes. Yes. So the question was, will the DRC complain because you don't have everything set up correctly, or the name nets and things aren't? So right now, yes, it will complain. We're trying to still figure out how to do it more automatically, but what we could do is if you give Circuit Painter your schematic file, it could look through to try to reference which part is what, and then copy it in. The way KiCad does that, I think, is it has references in multiple places that say, like, on the schematic, this part has a name, but actually KiCad doesn't care about the name, it cares about the UUID for the part. So you have to figure out what the UUID is. But it's all there, and it's all like in text, so you can figure it out. And of course, it's easy to script this.
For questions.
Oh yeah, okay, great, thank you. Yeah. We pass that back.
So is KiCad, is that your preview window to preview your code, generate your code?
Yeah. So what the program's doing is actually just spawning KiCad in the background and then showing it up. Yeah.
And is that quick, or is it like a little bit of wait?
It depends what you're doing and what computer you have. Like I have a Monster desktop, and it's very fast on that. On my laptop, it's maybe like 5 seconds for these kinds of sizes, so it's not so bad. Yeah.
Yeah. Okay.
It's definitely not automatic. So when I'm doing the web preview ones, those ones, it lags like 3 seconds before it shows you the new update. Yeah. Yeah. And I think it's also not clear to me what part of KiCad is slow there, whether it's like if we don't spawn a KiCad, like if you pop up the KiCad GUI, on Linux it's fast, on Windows it's slow. But if you just use the KiCad tool to generate an SVG, then it's fast. So there's a couple of things that you can do to play with it.
How straightforward is it to set up that toolchain, or is it included if you install the Python package?
So it's actually the one page I had there that had 1 command or 2 commands. That's it. So when you install KiCad on Linux using your repository, it installs the Python tools into the system Python environment, and then normally now, because Python has become more annoying, you have to create a virtual environment because otherwise it complains. But you can create a virtual environment that just points to your system setup, and then install Circuit Painter on top of that, and that's it.
Okay.
And so it's just one line. And on Windows, KiCad really helpfully makes this KiCad command prompt option, where they spawn a command prompt that sets up all the environment correctly to talk to KiCad. And so just from there, you can install Circuit Painter, and it's fine. And then that's it. Yeah. Yep. Okay.
What about DRC, design rule check? How do you make sure you pass it?
So right now, Circuit Painter prints out a warning if you don't pass it. It's not helping you. I need to get back to that actually, because the version of KiCad I was using like 6 months ago, if you call DRC twice from the engine side or from the Python scripting side, it would hard crash because of some variable that it made and didn't free and did again. But some time ago now they fixed that, so we can have an explicit DRC command now. Yeah.
But at least there is a warning, so you can set up CI. Every time you commit, it would just notify you, oh, this doesn't pass your DRC.
Yeah, and we might need to fix that a little bit. I don't know if I've got an exit argument set up correctly for that, but it's certainly possible.
Okay, thanks.
Yeah.
Anyone else for questions? Without further ado, thanks very much, Matt. That was awesome.
Okay. Thank you. I'll lock this up. Walking through speaker zones?
would you want to do but overcomplicate your home IT setup? So this next talk is going to be big data. We've got big data at home. Please join me in welcoming to the Hackaday Europe stage, Jan Ipma.
For it? Yes, there we go. Okay, so let's get into it. As explained, by day as my job, I deal with big IT systems, microservices, large development issues. But we're not going to talk about that today because I also have several hobbies that get totally out of hand, and one of them is home automation. And that's what I want to share with you today, like a little bit of my own journey, what I experienced, maybe the state of the art that we are in if you look at the hackable parts of home automation, and maybe some tips for people to pick up. So about 10 years back, me and my wife moved into our first home, and lots of new experiences. One thing with the electricity prices was that it was tenaciously hard for us to remember to switch off the lights when we're done doing something in one room or leave the house. And of course, rather than to remind ourselves, we need to find a technical solution for that instead. And that started with a couple of technologies that were sort of getting into popularity around the time. One of them you've all heard about, the well-known Arduino with the 80 mega chip on it that I suppose we've all seen at some point. One other thing was a system called FS20 that was actually birthed here in Germany. Have any of you heard of FS20 as a system? Ah, okay. Well, it was done by some electronics firms a while back, and was a approachable, cheap way to do home automation. It had a bunch of switches, some receivers, had a fairly simple protocol that they sent to each other, simple radio packets, and most importantly, it's either was documented or reverse engineered exactly how the protocol worked. It used something called on-off keying, which is basically you turn your transmitter on and off in a certain pattern, and it's fairly easy to pick up on the receiving side. Most importantly, it's also fairly easy to repeat or to do other stuff with. And that's where the third part of our triangle of technologies came in. There's a Dutch guy actually that made a little Arduino compatible board, but with a radio on it, in this case a radio from Hope RF, that talked at the same frequency, 688 megahertz, which a lot of other things also talk on, but it's the same frequency that FS20 uses. And even though that radio originally was meant for frequency shift keying, which is a different way to use radio, you can actually use it for on-off keying as well, because it's actually a simpler form of radio encoding. So, what does one do? Buy some stuff. Like I said, all this was fairly cheap, so it's not a big investment. And so it didn't take that long, both with the official buttons and with the G nodes, to control some lights. And FS20 also has some buttons that you can press on that send out radio signals to the receivers. You were able to receive those as well, but it turned out that there was this random pattern of noise that was received once in a while, like in the middle of a packet. And I couldn't quite figure out what that was, like where did these things come from? And at the time, the alarm system in our home used a set of components that you see there, which also turns out use wireless on-off keying at exactly the same frequency. And imagine doing your experiment, sitting there and moving about in your chair a little bit, and then suddenly noise comes into what you're receiving. That's how I realized, wait a minute, it's that motion sensor there that when I move, it sends out a radio signal and it's going to mess up my reception. Well, that's actually a good thing, because as it turns out, now we actually can use motion information, and we were working with the lights. So that's a fairly small step to say, okay, if I haven't seen any motion for whatever long period, then let's turn off the lights. So what did I do? Create some G nodes to work as a bridge between those RF signals that we see and some other computer where it's a little easier to control the logic, because I expected, well, the firmware of dealing with radio packets and receiving them, that's fairly static, but I'm probably going to be changing the rules on when lights should turn off and what should happen more often. So at the time, Java was my choice of language, so I wrote a little bit in Java that sat on a normal computer, a server, or a Raspberry Pi, I don't quite remember. And that sort of controlled the show and worked quite well. But one of the downsides is that the protocol for FS20 is so simple. You send out a radio signal to the lamp in this case, and if you're lucky, it got the packet and it turns on. But if you, I don't know, move around in the room at the same time, because the motion sensor sends something at the same time, then obviously it's garbled and the lamp will not turn on. And that's a bit of a limitation, which we will get back to. Now the system ran fine for a while until at some point, well, we had a little problem with our heating system. Now we have floor heating in the house, which is controlled through a central unit, and there's like a valve for every room that can turn on, and there's this box of magic that that steers it. Well, the magic escaped at some day by I think the switch mode power supply chip exploding or something. I looked at it. There was a bang, and well, no more heating, which kind of sucked, because if you then phone the people that made that, they say, oh yeah, we don't really make that anymore, and no, we can't really repair it for you either, but we'll happily sell you a new unit, and by the way, you need new sensors in all your rooms as well, because those have changed, and by the way, they're now wireless, and you need to replace batteries, and yeah, no thank you. So what's actually needed to turn on a valve for a heater? That's actually fairly simple, because you have this thing you put onto the physical valve, and a wire comes out with 2 connections. You put 24 volts on that, and it slowly starts to heat up some thingamabob in there that opens up the valve. It's fairly simple, because it sort of regulates itself. Either it has power and it turns on, and you remove the power, it slowly cools down again, and the valve closes. Well, we know something can do that. It's a transistor. You just put that on your microcontroller and profit. So what I set out to do is, well, let's take one of these G nodes, take one of the output pins, hook that up through a MOSFET to this valve, and see if we can control it. That worked fine. Then we need the other part, which is, okay, we need to know when to turn it on and off. Well, let's make a temperature sensor, put that in the room, and when it gets too cold, we turn it on. When it gets too hot, we turn it off. And the framework for that was kind of already there. Remember, we had these proxies that can receive radio signals and send them to our central software. So it was just a matter of reusing that same network, and well, heating was back. But I sketched a little diagram here to show you what we're dealing with now. We have our controller in the middle, and we actually now have 2 kinds of relays, because remember, the alarm system and FS20 was using on-off keying, but the normal radio signal for these radios on the G node was frequency shift keying, which is different. So we need 2 different proxies for that, and our temperature sensor sends stuff through one proxy, and then our alarm sensor and the actual buttons go here, and then we want to change the light. There are proxies the other way to actually make an on-off keying signal and send that to the lights, or make a frequency shift keying signal and send that to our heater. Kind of works, but it was turning into a big zoo. Plus, if the light doesn't turn on when you press the button, what are you going to do? You're going to press the button again, and then it will turn on. No big deal. But with the heater, you know, you really want to make sure it's on when it's on, and not keep sending signals all day long when it has to be on. So there, I needed to make a little protocol to make sure, like, did you get the message? Yeah, I didn't. Like this little thing back and forth. It was turning out not to be so much fun anymore. It started to look like work, which is not good. Now, luckily, around the same time, some other bigger projects were starting to grow. One of them being MQTT. Who of you have not heard of MQTT? Awesome. Oh, well, okay. Well, okay, sure. It is a way to broadcast messages from typically embedded systems to other things on Ethernet, like on a network. Most importantly, it is not a message queue, because it doesn't actually remember a queue of messages. It only remembers the last one, and then only if you ask it to remember it. So it's more of a broadcasting hub of topics than it is a queue. As you can imagine, that is a nice thing to have, because then you can sort of decouple in time sensors that send data and things actually wanting to receive it, or the other way around, you wanting to control something and that thing being around to receive it. You have this sort of broker in the middle that can relay messages back and forth. Another part is Home Assistant, which was also coming up right around that time, which is basically tries to do what my little Java program was doing before, being a hub for sensors and actuators around your home, typically, but not limited to that, which probably from it being Python-based is very approachable and very easy to extend with new functionality. If you go to Home Assistant right now, there's like hundreds of integrations for the weirdest things imaginable that you can just plug in there, and they will represent in a somewhat consistent set of sensors and ways you can change them. So those two things looked fairly promising, and sort of started me thinking, okay, I don't want to keep maintaining that Java stuff myself if there's something else that can do that for me. And that turned out to be a really good step, because the less code that you need to deal with yourself, the easier it is. Plus, Home Assistant back then and now even more, the automations that you make, so the rules that govern your home. If I press this button, then this light needs to turn on, or I have a thermostat here that is listening to this temperature sensor that needs to update. This switch, which is my heater, so it turns on when it's cold and turns off when it's warm again. All those things you can configure through a user interface rather than having to write code or even YAML files anymore. So it's fairly approachable. So there was one simplicity that helped out. Another development around the same time was the ESP8266, which is an interesting background. So for those of you that don't know it, it's a microcontroller with a Wi-Fi set on board, so you can hook it up to a Wi-Fi network, but it's also incredibly cheap. They're like $1 or even less these days for the actual chip. And the company originally made these chips for these USB Wi-Fi adapters that were very popular, where laptops didn't have it that much. But somebody in that company had the brilliant idea, okay, let's actually make this into a dev board, because then we can push Wi-Fi as an IoT thing a lot further. And that really took off, originally in China, but also further down, since the decision after that was that, for example, companies wanting to make a Wi-Fi switch or a Wi-Fi driven lamp, these Wi-Fi modules were so cheap that they would just take the actual dev board or that chip, put it in their end product and ship it with some strange Chinese firmware on it, but it worked. It was very easy to sell, very easy way to get out products. And then, of course, inevitably, since they all use this same chip, which is very well known, and the hackers among us have dev boards programming it, somebody was bound to write some firmware that says, hey, I want my own open firmware on this switch or lamp. I want to control it myself. And there were a couple of projects that started at Tesmoda, is one of the more popular ones these days. So if you combine that story, then let's do the same thing we tried with FS20. Let's get some of these products, some switches. Sonoff is one of the hardware manufacturers that makes these ESP-powered switches. You can get some Wi-Fi dimmers as well. And let's program them with the Tesmoda firmware. And it kind of just works. It is, especially these days, it is extremely approachable. No matter which switch you get, it is fairly well documented how you get Tesmoda on it. Sometimes you don't even have to open it up and make a serial connection. Some of them either have exploits or official support to get other firmware on there. So that meant a basic overhaul where we tossed out basically the old 868 megahertz components and put in Wi-Fi things instead. And it did a similar thing for the room sensors. But here I made a little circuit board to allow us to put like a temperature sensor and a humidity sensor and some other stuff in an easy way onto the ESP module. Another challenge there was that Wi-Fi takes a lot of power, obviously. but the chip can go to sleep, taking less power. The thing is that many of these development boards, and actually most of them these days, really eat away at power even if you're not using the chip. So you make the chip sleep, and then they have some stupid serial converter chip on there that just keeps drawing power or something else. So you have to kind of watch out which board you get if you wanted to put it to sleep and survive for more than a week. Well, I found one. It's the Wemos W1 Mini, which I selected and then made the circuit board for that to live on together with the other components. And that's now measuring the temperature throughout the house for the heating system. The one final thing that is good to keep in mind is we at some point had to change our alarm system because it was getting old and they wanted to have some new thing in, which was still wireless, but somebody at that company decided it's a really good idea to start encrypting the radio communication, which I haven't quite understood because it's a motion sensor. So either it sends out no radio data, or when you move, it sends out some encrypted packet that you can't see. Well, obviously somebody moved because, whatever. Somebody needed to tick a checkbox or something. Anyway, we didn't have the data on motion anymore, so we needed something fairly cheap to do motion detection ourselves. And one thing that actually, again, is fairly approachable is you have this originally DVB-T receiver chip, which again is fairly cheap. You can get one for $10 or something, just plugs into USB. It's originally meant to watch television. Nobody does that for that anymore because the chip can actually receive any signal from like 50 megahertz to 1.5 gigahertz and send it all over USB, and then you can decode it and do what you want with it. Which means that both the 868 megahertz band, but also the 433 megahertz band, you can just listen on that and then decode that with a computer depending on what you find. Which means that now you can, just like the proxies we had before, but now you have a very flexible way to look for similar simple radio signals. And one of them actually is motion sensors. You can get from China motion sensors that send out a very easy to detectable signal on 433 megahertz. Put those up, put a cheap USB receiver anywhere sort of somewhat close by, and you'll see whenever you send a signal from there. And again, you have a setup that is fairly open, fairly controllable, and you can steer yourself. Having set that up, things become a lot simpler because now, remember, the main communication is all over Wi-Fi, so there are very few relays or other things. Our room sensors send stuff directly to Mosquito, the MQTT broker. The lights directly talk to that as well, as our heater. Home Assistant sort of sits on the sideline looking at what happens in MQTT, provides a user interface to show what is going on there. Let me just quickly check my time because I don't have a clock here. Right. So what happened from there is that with Home Assistant growing and integrations growing and stuff becoming more available, basically anything that has a wire in the home and that is somewhat sideways connected to the network, you can plug into Home Assistant these days. I was going to demo some stuff, but the other laptop is not cooperating. So what I will try to do is show you a couple of screenshots instead of our Home Assistant setup. Oh, and I destroyed this one as well. This is just awesome. Yeah, that's what I meant. Can we, is it this? No, never mind. So for all the rooms in our home, we have a sort of a combination of sensors and other things where you can see, okay, what is the temperature? What are the lights doing? What are the timers for the lights doing? Has anybody recently been there? And you don't typically look at this, but if you want to figure out what is going on, it's a very nice way to get a quick overview, like what has last been happening in this room. Coming back here. Does anybody know how to make this full screen again? View. There. Yeah, I was gonna. Oh, there we go. L. L? Oh, for full. Yeah, okay. Because that makes sense. Okay, so so one of these things is Kodi. Kodi is a great way to watch the Blu-ray movies you already have, but in a more convenient way. One nice thing we can do now is when you start a movie, the lights dim automatically. When you stop the movie, they turn on again. Then RTV is I think one of the last 5 plasma TVs in the world that still work and haven't exploded. And on the back, we've mounted a couple of LED strips, and there's some nice software that looks at Kodi, what it's currently playing, and makes the LEDs glow up in the same color, which is nice. But it has this nice little MQTT integration that you can also just go into Home Assistant, select a color, and it will just provide some actual lighting for the room. Which again, if you want to dim the room a little bit, make it a little bit more, whatever your fancy is, you can integrate it that way. Then so typically for Denmark, solar cells have become more and more popular because of because of the high energy price that we have. The price not being the actual energy price, because that's pretty much the same all in Europe, but the amount of tax on top of it. So if you look at the price versus tax, we pay, depending on the time of day, about 3 to 10 times the actual energy price just in tax. And especially in the evening, this is to reduce the load on the net because everybody's cooking at the same time with electricity and there. Now, this means that if you're looking into solar cells, typically people get a battery as well, because then you can both cover the evening and night area, and it makes the whole thing sort of even out a little bit better. And there, when it was time for us to look into that, I explicitly looked, okay, can we get an inverter and a battery that is somehow, well, open-ish, like does it have an API, does it have a way to get information out of it and for us to control it? And the inverter that we have, it's from Huawei, it actually works really well. They have a fairly standard protocol called Modbus, and the documentation on how to talk to that. And because of that, there are actually, I think, several integrations towards Home Assistant for that particular setup. And that means that we can now use all information that we can find to actually steer our battery and solar cell setup. For example, the actual energy prices, well, the taxes are known, obviously, but the prices themselves fluctuate from hour to hour, but are published at 2 o'clock for the next day. So what Home Assistant now is doing for me is looking at the day ahead and looking at the energy prices there. It looks at the different web servers as well to see, okay, how much sun can we expect to get? It looks back in time, like how much sun have we gotten in the last 3 days, and then sort of tosses that into the air without any AI, I might add, and makes it a rough guess. Okay, so should we be charging our battery during the night because it's cheap there, because we're not going to get enough sun tomorrow? And that kind of decision you can really only make having a central thing like Home Assistant, because Huawei obviously is not going to implement that kind of logic, and even if they did, it would be, opaque and not really, you not really know what you do. And by having sort of all these data sources available, it's it's not fun implementing this. I mean, you have to write a combination of Python and this templating library that they have. It's pretty horrific, but in a way, it's good that it's horrific because it means that if you make something too complex, you probably shouldn't be doing it. So it's it's a good way to keep things simple. But it's pretty nice to be able to sort of push things around the way that you want it. And you can push that one setup higher, which is that, well, our car reached about 10 years, so we needed to look at a new one. And does it need to be electric? Does it not be electric? We went for an electric car, mostly because we had the solar cells, and we knew that especially during the summer, we would have some extra energy there that we wouldn't be able to use in the home or put onto a battery. And again, to have a charger for your car at home, assuming that you control it and there's no contract or leasing or other stupidity with other companies, I wanted to find a charger there where we could tell the charger exactly what to do and have an API that you can, again, have into Home Assistant to make sure that we can plug it and teach it things that it wasn't meant to do yet. And we found a really nice charger. It's made by GoE. I think it's a Swiss company. Again, put these two things together, and now it's possible to look at your inverter, look at, okay, we have so much sun that our battery is fully charged and our home is not using anything. Normally we would be giving the rest to the grid, but this exact rest of solar power, let's put it into the car instead. And this actually follows the sun like minute to minute. Like if the sun goes down, it will charge a little bit less. If there's more sun again, it will charge more. So it's a really, really nice way to use the extra energy and put it into your car. Unfortunately here, again, the feature that does that was not documented when I used it, still isn't documented. And I got at least 2 times the signs wrong here, like P-grid. Does that mean how much energy am I sending to the grid? So it's negative if I am reading from the grid, or is it how much I'm actually using from the grid? And it's negative if I push stuff back. And if you get it the wrong way, it will basically charge more and more as you pull more and more from the grid. Oh, more sun, and then put it into the, no, doesn't work that way. So again, documentation is fairly important, but at least there's the goodwill there. I mean, if you talk to them, there's support, and the company behind that, they want to be able for this to be open and for you to make it do what you need. Let's see, yes, I want to show a little bit about the data part of this, since that's part of the talk. So it's good to have all these sensors and have automations that control them, but I think where the real value is on having this centralized is actually storing your data. You've been told by many companies that data is important. It is, but it's even more important for you. Now, thing you can do in Home Assistant is use a protocol called statsd to send all of your sensors and stuff into one big database. And there is a software called Grafana that allows you to make really nice dashboards with that. I can show you some examples of that as well. Like here, for example, was it? There's a dashboard that actually shows all our solar cells performance and how it's running, when we think the battery should be charged, when we think the next car should charge, and all the statistics. And since this is software specialized for graphing and for data, it is much more responsive and much easier to dive into than Home Assistant itself. Yet you can still control everything through Home Assistant. So wrapping up, I would say that whenever you buy something for your home, do this little bit of research and see, okay, will I be able to integrate it? Even if you don't have Home Assistant yet, see, okay, are other people doing fun stuff with this light bulb or with this car or whatever it is that you're buying, and yeah, look into that openness, because I think will only get more important going on. Home Assistant will only get easier to use, and I expect there might be a future where this becomes simpler and simpler to set up. So thanks for your attention.
Thanks very much, Jan. If you have any questions, you can find him around, because it is now lunchtime. Those of you who are still sitting here eating, head on over. Who are still sitting here listening, head on over and grab something to eat. We'll start up the talks again at 1:30, and there is also Matt Ven's tape out workshop starts up at 1:30. So you got a little bit of time, chill out, eat, relax, talk to people, and then we're back on in an hour and a half. See you soon. Hey everybody, welcome back. Hope you had a good lunch. Next up, there's something, electric vehicles, electric charging is in the air these days. This is going to be another talk. Last one we had, Jan's talk was, charging his electric house. This is going to be how to charge your electric car in 2025. And with that, I'd like to introduce to the Hackaday Europe stage, Mastro Gippo.
Hello. Hi everybody, I'm Master Gippo. As a disclaimer, I make EV charging station for a living, but the opinions here represented are only mine. I've been working in the EV industry for about 15 years now, and do other stuff, mostly electronics. You may have seen some stuff of mine in Hackaday. Also, another disclaimer, I will make some gross oversimplifications here because the